our mistake?
Is it less than 0.2, so it can be
No.
I think it's we look at a refusal and like.
Yeah, I would look at the form. I would look at the Lagrange in your notes. Notes should be open anyway because we are in section 10.3. No, because it was the fourth degree Taylor polynomial.
Oh, gotcha.
No, it's okay. Keep thinking though. Where was our mistake? Look at the form of the Lagrange error bound.
Should it be 6 actually? I mean, no, that's right. I'm kidding.
Because it's the fourth degree, so it's supposed to be 5.
Everything looks pretty good to me. Or maybe a rush for 3. Yeah, I don't know. Oh, it's centered at 2?
It's, aha! Yep. C equals 2. What does that mean?
So you have 2, 3 minus 2?
That's really bad.
Because our error was way bigger than it was supposed to be. Because this one says, okay, let's say that the fourth degree approximation was 1.763. How is 0.4 with an approximation that's 1.763? That's tons of error. And then this one says, hey, could it be 1.778? Could it be 1.764? I'm guessing one of those is yes and one of those is no. And ours said it could be anywhere between like 1.2 and 2. We were having some major issues. C equals 2. What's the form of Lagrange say? X minus C, right? And what are we approximating it at? 3. So it should have been 3 minus 2. This wasn't a Maclaurin. It wasn't 3 minus 0. It wasn't x minus 0. It was x minus c. So that makes a big difference because then this is 1 to the 5th, right? Yes, please. And so we're trying to figure out what our error is within. It's going to be a lot different than 0.4. Justin, go ahead. Because Lagrange says that m plus first, if I can find the form of it, we are trying to maximize the m plus first derivative, or we need to maximize the m plus 1th derivative when approximating with the nth degree Taylor polynomial for the Lagrange error bound, for the worst case scenario. So if it tells us that, in this case, our 5th derivative, which is what derivative we're on, because we're looking at the 4th degree Taylor polynomial, the 5th derivative is what we care about, we can't just plug in the c like we would normally do, because that doesn't give us the Lagrange error bound. That could still be too narrow, meaning it might be an inappropriate bound, or too narrow of a bound. Instead, we need to figure out what this maximum value would be on the interval. And so when it tells us less than 0.2, we're going to use that as our, we don't need to know z necessarily. What we need to know is the maximum value of the m plus first derivative. So when they give it to us in this example, we say, sweet, plug it in, plug it in. So then if it tells us that the 4th degree Taylor polynomial approximation is 1.763, then it wants us to know the interval in which f of 3 must reside. If it's within, guys, couldn't that be above or below? Right? So then couldn't I just do my 1.763 minus r, good on the left, and 1.763 plus r on the right. So f of 3 is going to reside somewhere within. Yeah. Yeah. We can do it either way. That's okay. Seven, 6, 1?
Yes, yeah, the smaller one. And then the other one's 1.764.
Like your residence is where you live. Yeah. Where it equals, where it resides, where it dwells. I know, reside's kind of a weird way of putting it, huh? Where it will be, yeah. So then, I mean, in letter C, could it be 1.778? No, it's impossible. Why? Because it doesn't reside within the worst case scenario. It'd be outside the Lagrange error bound. However, could it equal 1.764? Yeah, totally. Because that next decimal place is a 6, so that would be within. Huh? Because 1.778 would be to the right, like on the number line. Yeah. So with that error, that we know that our actual function value will be somewhere within that. So besides messing up the centered at C part yesterday, we were doing pretty good, except for, well, actually, I didn't even realize that until today, the center. Being distracted by towards the end of yesterday. Okay, where does this interval come from? Any ideas? Why did they give us the interval 2 to 3? I mean, it's very appropriate because this is an AP question, and this is, as Justin was saying, this is crucial for the problem, or as he was asking, because it gives us the maximum value to use. So it was very particular that they gave us this interval 2 to 3. Yeah, if there was something with the theorem, like the intervals are important for continuity and differentiability and all that sort of jazz. But I'm more curious where it came from. Why 2 to 3? Not centered at 3, centered at... So we have our C as 1. Then we have the A as the other. Value that we're approximating it at. Remember when we're doing local linear approximation, right? We have our tangent line, we plug in our point, and that's our, I guess you could say our f of a and our a and our f prime of a. But then don't we have another x value that comes in later, which we usually call him C. The problem is now C has another meaning. C is the centered at, and A isn't being used for anything. So when we're trying to find R4 of 3, in this case, A is equal to 3. I'm just using A as a constant. I guess we could use B. I don't know. Well, because X is the general. So I don't want to just say X. I want to be like, no, the specific one that we're approximating at. Exactly. Isn't A the actual X value? It's not a distance away from an X value. So when I changed Lagrange error bound back here and I was saying plus A minus A is an actual location. A is an actual value. It's not a distance away. So this doesn't make sense. I know. I changed it to... Well, anyway.
So it should be A minus.
Well, what'd you just see, though?
Oh, it's C and A.
C is the center. And A is where we're actually approximating. So if you were to actually see the A, I mean, this could be a little bit helpful. You could think of R sub n of, if we're actually doing an approximation, we're actually plugging in an A, right? So then we could actually be thinking of over here in our formula, just so that we have an A, because Riley, as you were asking earlier, you're right, I didn't really write in an A over here. If we're actually trying to approximate using the nth degree Taylor polynomial, we're going to be plugging the A in over here, right? If I can actually get pointing to the X. But that would be when X equals A. Now we have our A introduced. It's the value at which we're trying to use the polynomial to approximate the function. So that's if we're approximating f of A. Then the error resulting from plugging in the A, x equals A. Now we can go ahead and say that we're talking about the interval either, and here's the idea I was trying to show, it's just not going to be very nice. It's either C to A, but does A always have to be above C? So what I was trying to show was the idea that A can be above or below, but addition and subtraction was not the appropriate way to show that. How am I going to have to show that? Is sadly by saying the word or. It depends on the context as to whether A is above or below. It's awkward, I apologize. It is that idea of A being above or below, but it's not a distance that I'm adding or subtracting. Instead, sometimes you're going to be approximating above wherever C is, and sometimes it's below. So your interval is going to be formed by the center and then wherever A is, and just put it in the appropriate order as far as who's less than, who's greater than, exactly where you put it. So in the one we just did, 2 was the center, 3 was where we're approximating, so the interval is 2 to 3. But if it was something like 2 is our center and we're approximating at 1.5, well, the interval will be 1.5 to 2. C is going to be on one part of the interval and A is going to be on the other. Just make it appropriate. Does that kind of make sense? Yeah. Sorry that I used addition and subtraction when I should have just used an or. I was trying to make it nice and pretty and summarized, and it didn't exactly work. Okay. Whew, now we have that one good to go. I know, awkward. Took a while. We're there. So now I'm curious. As I go ahead and get your 10.2 evens copied into Google Classroom, because obviously we didn't really feel the lack of them last night that much. So then this weekend we can work on 10.2, 10.3 and go over questions, homework questions on Monday. I just want to see if you guys in your groups can tackle a free response-ish question dealing with Taylor series and at the end Lagrange. Sound good? I'm not sure if I feel confident enough that we're ready for a competition on this. But let's see how this one goes. Let's see how this one goes. Is that good? Okay, ready, set, go. Day of the fast. It's all right. So I'm going to start playing with it. I think so. What you were saying sounded good. All right, guys, I'm going to start playing, but feel free to keep working.
Tried to do this. So like the way I did it was I did like the sine plus the cosine every time plus cosine. It's the same thing because it's addition.
Okay. How do you guys think about my spectrals? So I started with what sine of x would equal. I went to what sine of x squared then would have equaled. So if you want, you can actually think, okay, I don't need that anymore. I'm trying to put together sine of x squared and cosine of x. The nice thing is, since they both are polynomial terms, couldn't I just... So then, sine of x squared plus cosine of x. What do I mean by in order? Polynomials, I need ascending order for my Taylor. So ascending order, 1 doesn't combine with anything, so sweet, it's 1. Ascending order.
Oh, I just did decent.
Well, but you can't do these, they build up. All Taylor Maclaurens build up. F prime, F double prime, F triple prime. Does that make sense?
Why is that necessary?
Because if I'm trying to find the sixth derivative, I need to think of, okay, F of F prime of F double prime of F triple prime of. Does that make sense? So then as I go ahead and combine, I have a 1x squared and I have a minus 1/2 x squared, which will be 1/2 x squared. True? So then I've gotten this one, I've gotten that. Now I have an x to the 4th over 4 factorial, right? And then what else do I have? I have a minus 1/6 minus 1 over 6 factorial, which would end up being 6 factorial. Is that 720?
I think so. Yeah. 120 times 6.
A 1/6, which would be 120 over 720? So negative 121 over 720?
We have to simplify like that.
Is that right?
So, it's minus in the middle.
And guess what? I have 1, 2, 3, 4, so I don't need any more, right?
So once you just have 4, you just disregard.
I mean, you could have kept going, but I'm fine stopping where, yeah.
You look
So
at less
even
than-
though you just included in the sign, you just disregard that.
Well, my objective wasn't the sign. My objective was the sine of x squared plus cosine of x. So I just put out as many as I was like, I don't know, I'll do a few, right? And then I'm like, okay, I only need the first 4 of my overall series. Or actually, I'm only supposed to have my first 4, so yeah, we do need to stop. Now, why are they asking me in letter B for the 6th derivative?
Find the Taylor.
Because I have the 6th degree term. And if Riley had kept going, and if she had found f and f prime and f double prime and f triple prime, and if she had plugged into all of them, she would have gotten this exact same thing, which means this 6th degree term has what in front?
I thought that was the 4th derivative. I thought you just said
Wait. But you're stuck in what it was before it was put together. If Riley had found 6 derivatives, she wouldn't have done any of this trickery to get here. She would have done it the long drawn out way, and she would have ended the 6th derivative being this term. Because remember our Taylor polynomial? This term right here would have been the 6th derivative of this function of 0 all over 6 factorial times x to the 6th. Now, we were able to skip here. We were able to jump ahead here using some special series, some special Maclaurens. But ultimately, if she had done 6 derivatives, she would have built this term from the function, not using any of this. So they're asking not for the 6th derivative of, 6th derivative of, they're asking for the 6th derivative of this function at 0, which is contained in this term. Is it this term? No, because what else was put into the formula? The 6 factorial. So what do I have to multiply both sides by? The 6, oh, well, hold on, but isn't 6 factorial 720? So what is my 6th derivative of 0 without me having had to derive anything? It's negative 21.
I like that.
Because this term, if I was to, which this is all not trickery, this is all using our special Maclaurens to build a Taylor polynomial without actually finding our first derivatives. Oh, well, actually, that would have been our f of. If you plug in 0, sine of 0 is 0, cosine of 0 is 1. This is f of 0. Our next term, which Riley did do, right, the f prime, if she found f prime and she plugged in 0, she ended up getting 0, which is why our x to the 1 term is gone. If you had found the second derivative using her derivative, which product rules and craziness, you wouldn't have wanted to, and plugged in f double prime of 0 over 2 factorial times x squared would have ended up being f triple prime ends up being 0. It goes away. F quadruple prime ends up being over 4 factorial times x to the 4th, 1 over 4 factorial. The 5th derivative being 0. 6th derivative ends up being negative 121 over 6 factorial x to the 6th. So if you were actually deriving those crazy derivatives, and Riley was like, wait, I don't like this. Hannah in the homework section 10.2 was like, my derivatives are ways of skipping ahead, but the meaning is still polynomial. This is the 6th degree term. It means the coefficient of the term is equal to the 6th derivative of f of 0 over 6 factorial, so I can solve, and figure out what the 6th derivative is. I can basically be a little human calculator without actually deriving. Oh, well, I'm sorry. I could have done x to the 6th and x to the 6th, and then I could have gone ahead and divided by x to the 6th if you want. But I'm just looking at the coefficients because that's where the derivative resides. So I could have written this whole thing out. Sorry, because it was the same on both sides. I only looked at the coefficients. Does that make sense? Now, what's going on in letter C? Let P sub 4 be the 4th degree Taylor polynomial for f about, wait, 4th degree? That's not this whole thing then, right? Wouldn't you have stopped early? So the 4th would have just been 1 plus x squared all over 2 plus x to the 4th all over, I mean, I guess I could multiply it out. I'm just being lazy. It just ends up being 24 anyway. But let P sub 4 be the, got it. Using the information from the graph, show that P sub 4 of 1/4 minus f, isn't this just error? The approximation minus the actual? Show that it's less than 1 over 3,000. Well, it's not alternating, so I can't do the alternating series, so I must be doing Lagrange. Oh, wait. Lagrange. If I'm trying to think about the error, let's build it. The error from the 4th degree of 1/4, right? Wouldn't that be the 5th derivative of, I need a maximized over 5 factorial times, it's centered at 0, right? So x minus 0, and x is 1/4, all raised to the 5th. Oh, dang, I can't do Lagrange unless I know the maximum value of 5th derivative of f on what interval? Centered at 0, going to 1/4. There's my C, there's my A. Do I have a 0 and 1/4 over here? Yeah, I do. Isn't that my 0 and isn't that my 1/4? And who is this guy? The 5th derivative. Where is he maximized? At 1/4. What is he? I don't know. He's less than 40. Pause. Should I say 30? Should I say 20? Not 20. Should I? 40. Remember, in that little important thing, it's not always reasonable to know exactly what it is, so we have to at least do like the worst case. What do I know that this is below? 40. Okay, so let's see if this works. Are they being mean? What would be, wouldn't be equal, be less than. Oh, less than. Okay. 40 over, isn't 5 factorial 120? And this would be 1 over 4 to the 5th? What's the dilemma? Do we really want to do this math? You could make that one thing. And you could say that that's 16 times 16 times 4. Or 256 times 4. Because that's 4 cubed, and then we have another 4. So we have 4 squared, which would be 16. which is 256 times 4. Yeah, what do you get? 1,024 times 3, which would be 3,000. And now pause. It's something bigger than 3,000th, right? Uh-huh. So how do we bring in that number? He's bigger than all this, right? So guess what we could do? As long as we did it right. As long as we did it right and we're confident we did it right. They don't need to see all my work where maybe I make a mistake with my multiplying, do they? Can I just be like, oh. You don't actually have to get what that is. All you have to do is be like, I'm confident I'm right. Ha ha! Done, 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 done. It's a nice trick. Because if they plug that in their calculator, it's less than 1 over 3,000. 1/3000th. I just don't know why my brain couldn't do that. Bye. Lagrange. Uh-uh. Well, you have to show your work with Lagrange. But you could literally guess and be like, well, I did it right, so it better be within. All right, cool. Dun, 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 dun. Yeah.
Would this be like in the calculator problem?
Yeah.
So would you get partial credit if you did all the top stuff right, and then if it's not greater, it's not
Well, hopefully you would like look at this and be like, I know it's supposed to be, so you kind of fudge it anyway. But yeah, you would get partial because with free response, it would probably give you something for the form of what I've seen point for the form of the Lagrange error, and then like actually you knew what to do with the graph and plugging in. Yeah. Yeah. So that's what your conclusion needs to be, whether or not you fully get there. I mean, at least state it and be like, yeah. Yeah. Okay, so what's going on with this guy?
Why like you give me a sign?
They could have given you sine or e or cosine or ln of 1 plus x or 1 over. How bad does this one look? Yeah, it's not too bad, right? It's a sine of x. We're just going to use our special Maclaurin. Okay, so hold on. How about this guy? We haven't done an e yet.
Well, there's an E1, isn't there?
Yeah, what is the e one?
It's 1 plus x. Oh, you want to tell you?
Right? Factorials or no factorials? Factorials. Who doesn't have factorials? Oh, they don't? Wait a minute, why did it show 5 terms? It said fourth. No. Doesn't say, okay, so are we seeing the difference in how they're wording the question? It's a 4th degree. It doesn't say the first 4 terms. The last one said the first 4 non-zero terms, which ended us at the 6th degree, which was weird. So just keep an eye on the wording as to what's going on. Right? It says to then use your polynomial to approximate e. Wait, what? Exactly, e to the 1, so when x equals 1. So I can do e to the 1 is approximately p sub 4 of x equals 1. This is the Maclaurin, so we know it's centered at 0, which is why I didn't do any like subtracting stuff, right? So I could do 1 plus 1 plus 1/2 plus 1/6 plus 1/24. Right? Couldn't I make these all like 24ths? So I could do 24 over 24 and then 24 over 24, and I could do 12 over 24 and then 4 over 24. What would that be? 48, 60, 65 24ths? that look about right? 24, 48, 60, and 65. I think it's 65 24ths. But then it says find a Lagrange error bound for the maximum error. We went up to the 4th degree, so Lagrange says what? Does that make sense? Because it was e, so e is e to the 1, so when a is 1. So then I'm plugging in my a here, which means which derivative of z, all over 5 factorial times, 1 to the 5th is easy, because that was my x minus, my a minus c, or my 1 minus 0. What's my dilemma? We don't have the 5th derivative. They didn't give us a clue for the 5th derivative. Good thing the 5th derivative is exactly what all the derivatives are. What's the 5th derivative? A lot better than either of the ones that you two had to suffer through, and they're awful derivatives. It's just e to the x, e to the x, e to the x, e to the x. Oh, so wait a minute. What's the maximum? Hold on. I need to maximize this guy on what interval? Who's my C? Who's my A? Remember? Where are you centered at? My 1's above. So I'm just looking at 0 to 1. Wait, we know E. What does E do? Swoop, there he is. Oh. Isn't he maximized at 1? Because he's high at 1. So the Lagrange error bound is defined by itself. Anybody catch the irony? You're approximating e to the 1. To approximate the error with e to the 1, what do you have to use? I don't know e to the 1. That's the whole point. I mean 2.71828. But as far as like this approximation, I'm defining the error for approximating e with e. This is one of those cases where you would say, okay, well, what do we know e is lower than? Huh. We can't do 2.5 because that'd be lower. It's 2.71828 because of what we know. So 2.5 would make the error bound lower, so then it could actually be the actual could be outside of. We could do 2.8, like what we know. We could do 2.8, but the 8 expect you to do like decimal, be like, e is less than 3, sign less than 1, close less than 1. You'd be fine. But if you have to actually like do mental math in order to check something, you're not doing e, just use 3, if that makes sense. So then what's an interval that e would actually fall in between? Yeah, use our approximation, right? Sorry, on the left-hand side, it's not adding. What is it? Because 5 is 120, and then 3 over 120 is 1 over 40, yeah, if we reduce it. How would you have simplified 2.71828 over 120? So that at least gives us some sort of idea. And technically, we can actually even say that it wouldn't even be or equal to, because we just chose something even outside the worst case scenario. We made it a little bit broader just for sake of being simple on our minds. But that's a case where if you get like something awkward with sign between like 0 and, I don't know, 1/2, pi over 4, 3 point, yeah. If you had something like we were trying to maximize sine of x, let's say he was your derivative and you were trying to do on 0 to 1/2. Don't you guys know that sine 0 to 1/2, this is pi over 4. Pi over 4 is 3/4-ish. So 0 to 1/2 is from here to here. Where's the maximum of this? Sine of 1/2. Well, what's sine of 1/2? I don't know what sine of 1/2 is, but what is it definitely less than? It's less than 1, so we would use 1. We wouldn't use some awkward decimal that we don't know. Some people in previous years have gotten really mad, being like, you have to use e to approximate when you're approximating e, that's dumb. No, we would use some sort of nice, easy number that we know e is less than. Arian.
So if we are like doing that one over approximating, why is it not wrong just to put equals? Because then isn't that technically not a true statement?
I wouldn't say it's wrong to put or equal to. I would just say it's more appropriate to take away the or equal to because our bound is even broader than it needs to be.
But if we left equals, would we get rid of
No, I don't think so. I think you're all right. Not always, but you know how in AB you could have a volume FRQ where that's kind of how Lagrange is. But usually Taylor polynomials will be a part of an FRQ. Sometimes Lagrange shows up in it and sometimes it doesn't. It kind of depends. I don't think we're going to do this one, but guys, we already looked at something similar to this where they could be giving you the clues for the derivatives and you build a Taylor polynomial out of it. You approximate, oh, hey, whenever you see this, it's Lagrange. They're showing you the maximum value, like that 0.2, Justin, that you were saying just a second ago, and then you're using it. So I was just trying to show you guys some Lagrange AP practice. I think technically, even on our calendar, if I was to go there as far as my goal for today, it was the Lagrange error bound, and it was specifically AP practice. So the nice thing is we're actually not really all that behind. I wanted to try to start 10.4, 10.5 today, but kiddos, what's due on Monday? Sorry, that's what we're doing. Homework on 10.3, what's already been due? Section 10.2. So let me show you what I did in your Google Classroom as you guys were trying that one and getting a bit perplexed and a bit confused, but hopefully we're better now. In your homework number 44 and 45, 10.2 and 10.3, what have I posted? Okay, so for 10.2 and for 10.3, I've gone ahead and put the evens in there, the calc chat-ish, because you guys haven't been getting calc chat, for 10.2 and 10.3. Now, do you have the odd calc chat-ish without going to Slater? No. But you have the answers right in the back of the book that you can check. So what's our goal on Monday? Have 10.2 and 10.3 ready to go and questions narrowed down on odds and or evens, because maybe some of the evens solutions, I mean, calc chat, you guys know, skips ahead, magical steps, etc., etc. Are we kind of cool, though? Do we need to keep those special Maclaurin series close? They're our friends, not our enemies. You might even want to start memorizing. Bye, cool kids. Thanks for hanging in there today, even during the painful parts.